Assalamualaikum. My name is Adan and I will be starting our project. So, first of all, you can see these are our four group members, and let's move on to objective. So, our objective was to apply some traditional image processing methods on real world images. So, we used six different images from cityscapes dataset, and we kept these images in full resolutions. And later on, we will be applying some different methods on them. These methods are spatial filtering, frequency filtering, segmentation, and at last object detection. And my other fellow will cover the conclusion part. So let's move on to the code. So this is a structure of our project. We use different files, and so let's move on to the code. So this is our code, and we are applying code on clone image, and this is you can see we use three filters here. These are mean filters, Gaussian filter, and the third one is median filter. So let's and that's how we display the results. So let's run the code. So as we can see the difference in all the image. So let's move on to the output images. As we can clearly see that the images here are not very visible. So, so these are the images, and so as we applied the code on clone images, so let's see these images. And so this is the Gaussian filter, as you can see, and this is the mean filter, and this is the, as you can see, median filter. So now let's talk about some uh, other pictures. This is the Gaussian filter, and then mean median filter. And now some of the other pictures. This is the Gaussian filter as usual, and this is the mean filter, and this is the median filter. And the last image, same as this is the Gaussian filter, and this is mean, and this is a median filter. Okay, so now we should talk about uh, the strength and weaknesses and the best use of these filters. So for mean filter, the strength we can say that it is used for simple smoothing. It reduces random noises, and its weakness is it blurs edges and some fine details. So the best use case is basic denoising. And about Gaussian filter, it smooths the picture while preserving it, and its weakness is that it loses some edge sharpness, and its best use case is its natural looking blur. And for the last filter, the strength of median filter is it removes salt and pepper noise without blurring edges. It is slower for larger images, so we can't use large images for it. And its best use cases impulse noise and maintaining object boundaries. So I would say that median filter is the most effective one. So that's it from my side. Allah Hafiz.
Hello everyone, I am Hamza and I will be explaining the second step of our pipeline, which is frequency domain filtering. This method gives us a different perspective of the image. Instead of instead at pixels directly, we analyze the image based on how fast the intensity changes across the image, known as frequencies. Implementation. First, we converted the image into the frequency domain using the 2D discrete Fourier transform. This helped us understand which parts of the image had high frequency details like edges or low frequency areas like smooth surfaces. We used three types of filters. Low pass filter, this removed high frequency components like noise and edges. The result is a very smooth image but with loss of fine detail. High pass filter. This did the opposite. It removed smooth areas and enhanced edges, useful for highlighting transitions and textures. Third one, band pass filter. This kept only mid-frequency details, filtering out both the very smooth and very sharp components. Now we will look at chords. Frequency low pass. ये नाम है लो पास फिल्टर में हमने से कर दिया है. अब इससे जो आउटपुट्स आ रहे हैं वो इस तरह से आ रहे हैं, like this. इसके बाद हमने चेक करना है हाई पास फिल्टर. इसके हम कोड देख लेते हैं. रन. इसके जो आउटपुट्स हैं वो इस तरह से आ रहे हैं. Now अब इसके बाद हम देते हैं बैंड पास फिल्टर. इसका कोड एंड देन इसे हम कर लेते हैं. इसके आउटपुट कुछ इस तरह से आ रहे हैं. अब हम इसकी आउटपुट देखते हैं. हमने हमने इन कोड्स को डिफरेंट रेडियस के साथ हमने चेक किया था. अब लो पास फिल्टर विद रेडियस 30, उसमें जो हमारा आउटपुट आ रहा था वो इस तरह से आ रहा था. देन विद रेडियस 50, उसमें आउटपुट हमारा इस तरह से आ रहा था. देन विद रेडियस 80, उसमें जो आउटपुट था वो इस तरह से आ रहा था. देन हाई पास फिल्टर विद रेडियस 30, जो आउटपुट था वो ऐसे आ रहा था. विद रेडियस 50, आउटपुट ऐसे आ रहा था. नाउ एट लास्ट विद रेडियस 80, उसमें आउटपुट ऐसे आ रहा था. इन द एंड विद बैंड पास फिल्टर, उसमें जो आउटपुट इस तरह आ रहा था. इसमें जो हमारा रेडियस था वो 30 से 80 तक. Low pass filter was most useful for noise reduction but blurred the image significantly. The high pass filter was best for edge detection but more the image too sharp and noisy. The band pass filter gave a balanced result. It preserved key structures while suppressing streams. So overall, the band pass filter gave the most visually usable result for urban scenes, especially before segmentation. In the end, that concludes the frequency domain part of our project. This step helped us understand which frequency components are important for structure and detail in the image. Now we continue to further.
Assalamualaikum. I am Fatima and I will cover how we simulated noises image and restored them using different filters. We have image restoration. We added three type of noise to images. Gaussian noise for smooth random variation, salt and pepper noise for sharp black and white speckles, speckles noise for graining texture. Then we use two restoration filters, median filters for salt and pepper noise, adaptive Venner filter for Gaussian and speckle noise. First we have Venner filter. And last one is adaptive Venner filter for Gaussian and speckle noise. Now we have here is a comparison between original noises and stored images. The results show how different filters work with different type of noise. Salt and pepper noise with median filter. The, comparison between original, noisy, and restored image. Last one was now we are moving to image segmentation. That's all from my side. Thank you.
Assalamu alaikum everyone, my name is Zauraiz Ahmad and I am here for the last section, image segmentation, object detection and compression part of our project. So let's first take a look at our first segmentation technique, the canny edge detection. Let's apply this on our MATLAB online. Here's the code, we applied this on the Bremen image, we converted it to grayscale and then applied the canny edge detection. Let's run the code. Here's the output. So in segmentation, our goal was to divide the images into meaningful regions and identify objects like vehicles or pedestrians in busy urban scenes. Let's take a look at other outputs we got by applying canny edge detection on other images. So this is the output on the Bremen image. As you can see, the objects are easily identifiable. It detected the boundaries very well. Let's move on to the next image. Here, as you can see, it worked perfectly well here. All the cars are easily identifiable. All the edges are easily identifiable. Alright, so next image. So this is the image from Hamburg, Germany, and it was a complex images. As you can see, Kenny's detection failed here to give us meaningful results. This image was too complex. There are three pedestrians walking, and in the background there are many trees. It worked relatively worse from the previous two images. Alright, let's move on to thresholding. So first, let's take a look at Otsu's thresholding. We applied this on a Hamburg image. Otsu's method automatically selects a single threshold value, and it only works better in the well-lit high contrast images. Let's take a look. Here's the Hamburg image. It failed to produce meaningful results. You can see it blacked everything that was in a shadow and only kept the well-lit part of the picture. Let's look at the other outputs. Here's the colon image. It blacked everything as everything was in the shadows, only kept the well-lit parts of the image. Let's move on to adaptive thresholding. This was the most successful technique in our project. It computes local threshold across the image, which work great for uneven lighting and complex urban scenes. Let's run the code. Is a code applied on the colon image. The adaptive threshold value here we set this to 0.5 as it gives the best results at this value. Let's run the code. Here's the comparison with the original grayscale image. Let's open the outputs in a better picture so we can easily check that all the objects are detected. Here you can see all the objects are clearly identifiable. We can tell multiple cars here are on the left and the right of the image. Let's look at other picture. Here we can already see that it worked better than Kanye detection here. It detected pedestrians and it was overall the best technique we applied. Let's move on to the next segmentation technique. So let's take a look at our other segmentation techniques. So first we'll check the watershed method. So basically we use the marker control watershed segmentation. Here marker control watershed is a method that tries to separate objects in an image by imagining the image as a 3D surface, a topographic surface like hills and valleys. The bright areas are peaks and dark areas are valleys. It works by simulating water flooding from the lowest points called markers and growing regions until they touch each other. These markers are manually or automatically selected points where we know a certain object or background starts. So when two growing regions meet, a boundary is drawn. This is how it separates object. Let's run the code. So unfortunately, this method didn't perform too well on our images. It produced color gradients but failed to isolate real world objects like cars or pedestrians. So here is our code. It, we applied this on the colon image. And here we applied Gaussian filter. Then we did adaptive thresholding. After that, we did morphological cleaning from I'm open and I'm close. So I'm open removed small specks, small dots on the image. I'm close filled the gaps, and I'm filled the enclosed holes. Here we applied watershed. Alright, let's look at the other output from the watershed. It didn't produce any meaningful results. Let's take a look at the other segmentation technique, the connected components analysis, where we detected objects and counted them. Here's the connected components code. We applied this on the colon image, then the adaptive threshold. After that, we did morphological cleanup and then applied connected components, where our region props we set on bounding box, area, and eccentricity. Alright, let's run this code. So it worked better than watershed, especially on the two images we decided, but it still detected a lot of small irrelevant objects like random spots in the images. Even after we applied area filtering, it counted many false positives. Here you guys can see. Let's look at other outputs. This was the final labeled one. We labeled each and every object. It detected 49 raw objects. Alright, and this image. So overall, it didn't quite work well as we were expecting it to be. So we thought there was a problem with our code. So to ensure that, we tested the same codes on a simpler image like coins from MATLAB, and these codes worked pretty well. Here's the watershed result. This was the original grayscale, and at the rightmost watershed result, it worked quite well here. And this was the connected components one. It detected 10 objects easily. So the main issue was that our images were too complex as they were simulating real world images, like uh, there were different contrast and light problems. Now let's move on to the final image compression. Let's quickly run the code. So this is our code. We applied this on the colon image. So we did JPEG compression and set the quality to 30 so that the image retains all the details. Let's quickly run the code. So here you can see that the original size was 2095 kilobytes and the compressed size is 77 kilobytes. The file size dropped by over 80%. Here are the PSNR values: 39.65 decibel and SSIM was 0.962 bit. Alright, so let's jump to the conclusion. So to conclude, our project successfully implemented a classical image processing pipeline using MATLAB Online. Adaptive thresholding and canny edge detection were the most effective segmentation techniques. Watershed and connected components didn't work well on complex urban images, but worked on simpler test cases. Compression showed that large images can be efficiently stored without major quality loss. We also preserved all images in the original resolution 2048 by 1024 without resizing so that the object details remain clear. So this project helped us understand the real world limitation of traditional methods and gave us valuable hands-on experience in image processing and visual analysis. So to take a closer look at our project, you guys can visit our GitHub repository link. I'll provide the link in the description. Here's our project and here's the latest report of our project. And alright, so that's all from our project. Thank you. Allah Hafiz.